Excellent. Okay, so we'll begin. So yeah, my plan today with you guys is to work through this 2020 sample exam. So this is an exam that they put together at the end of the 2019 course. So that's when they changed from 3-hour exam to a 2-hour exam. And the purpose of it is just to illustrate the complexity of a 2-hour exam. Yeah, there's those two there. Where's my copy? Probably not there. Excellent. So yeah, our plan today, work through it. And what I anticipate, this is a 2-hour exam, but I reckon we can probably get it done in well under 2 hours. So it sort of shows that you can work through something very thoroughly and then have a bit of time at the end for checking and so forth. So this is both booklets combined. I'll be referring to at different times to our textbook and to our different notes books. So that might be a good chance to figure out what kinds of things we should be writing down. But we start off with a nice easy question. So let's get right into it. We have a vector question here. We have a rhombus. Okay, so this is it's a parallelogram with equal sides, right? That's what a rhombus is. We have O, P, Q, and R. And we have vector from O to P is defined as P, and vector from O to R is defined as R. And part A1, find OQ, find the vector from O to Q in terms of P and R. Well, if this is vector R and it's a rhombus, it means vector PQ is also vector R, right? And so then the vector from O to Q is just going to be P plus Q. So 1 mark for writing that in there. On to B. G'day Hayley, grab an exam, grab a seat. And we've just begun, running a little bit late. Okay.
It would be P plus R.
Yeah. P plus R, thank you. That's not vector Q, that's vector R. P plus R. Okay, find the vector from P to R in terms of P and R. So from P to R, that's going to be negative P plus R. All right. And then we'll scroll down. Show that OQ dot PR equals R squared, modulus of R squared, take the modulus of P squared. Okay, so one thing we're going to be using here is we're going to be using the vector property that A dot A is equal to the modulus of A squared. All right, so that's a vector property that we're going to apply here. Now, the way we're going to show it, we're asked to evaluate vector OQ dot vector PR. So the dot product of those two vectors. Now we've already found vector OQ, that's P plus R. And we've found vector PR, that's going to be minus P plus R. And we're just performing the dot product of these. Now dot product is almost the exact same as like a FOIL method here. What we're going to have is we're going to have P dot negative P. Okay, so we're going to put that as negative P dot P. All right, then we have P dot R. Then we have R dot negative P. And then we have R dot R. All right, so we're just performing the FOIL there. And so then what we'll be left with, we've got R dot P here and R dot P here. So we've got the positive and the negative. They're just going to cancel, okay? They are like terms that cancel each other. And so we're left with negative P dot P plus R dot R. And now applying this vector property, we get here the modulus of R squared. And applying this vector property, we have the negative modulus of vector P squared, which is the modulus of R squared. Take the modulus of P squared, QED. All right. So then we have have B part 2, so maybe I'll fix this up. This is A part 1, A part 2, this is B part 1, and then we have B part 2. Hence, okay, hence, whenever you see hence, this goes for methods as well, means using what you've just done. Prove that the diagonals of a rhombus, of the rhombus OPQR, are perpendicular, giving reasons. Okay, so the diagonals are going to be perpendicular if the dot product is 0. That's a property of dot product, right? If the dot product is 0, so let's make that argument. We're going to say if, then we have OQ, if OQ is perpendicular to PR, then OQ dot PR equals 0. Okay? And then we'll say something like this. Now, OQ dot PR equals modulus of R squared, take modulus of P squared. That's what we observed in B part 1. And because, g'day Seth, a little bit late.
Yeah, kind of slept in a bit.
So we've grabbed an exam, we've just finished question 1 pretty well.
Is this a sample? Yeah.
Yeah.
I was looking for it before I came and I was like, oh, I don't have that.
Nah, all good. And because OPQR is a rhombus, therefore the modulus of R equals the modulus of P. Alright, and so therefore OQ dot PR equals modulus of P squared, take modulus of P squared, which equals 0. Now I've really drawn that argument out there. It can be simplified a little bit, but that's quite clear communication of our argument there. Alright, anyway, I reckon jump on to question 2 and join us at question 2. I think Hayley, you caught up pretty well? Yep, excellent. Okay, so here we have a curve with parametric equations. Part A, draw the graph. So we have x of t is the square root of cos t. And we have y of t is the sine of t. Alright, so type that into parametric mode, square root cos t sine t, and make sure we restrict the value of t from 0 to pi on 2. And we've got 1 here and 1 here, and it's just doing this. Okay, so we get 2 marks for sketching that. So we've got to make 3 marks, that's a very generous 3 marks. Make sure we have the correct location of these points. Now we're presented with a blank axis, so when they're allocating the marks, all right, a lot of the time, probably 90% of the time when you're asked to draw a graph, you'll be provided with an axis, so you'll be provided with the numbers on the axis, and it's just up to you to draw on the axis. Because we don't have the numbers here, that means we're expected to put them on. Okay, so we need the numbers, we need the correct shape, and that'll get us the 3 marks. Okay, part B. Show that the points x and y on the curve satisfy the equation x to the 4 plus y squared equals 1. Okay, so all we're going to do is we're going to say if we have x to the 4 plus y squared equals 1, so this is part B, let's take the left hand side, is x to the 4 plus y squared, and based off of our parametric equations, this is going to be the square root of cos t to the power of 4 plus sine t to the power of 2, which equals cos squared t plus sine squared t, which equals 1, which is the right hand side. If I'm going too fast, or you got a question, please ask me to go a bit slower. Okay. Next, we have use implicit differentiation to show that the derivative dy on dx is equal to this. So we're going to use implicit differentiation with regards to with regards to x to differentiate this function here. So we have x to the 4 plus y squared equals 1, and we're performing the derivative with regards to x of the function. Okay, that's what we're asked to evaluate in part C. So the derivative of x to the 4 will be 4x to the 3. The derivative of y squared will be 2y dy on dx. Okay, so going back to our most recent test on differential equations, I've got those to hand back to you, by the way. I've been hanging on to them, so make sure I pass them back to you today. And the derivative of a constant is 0. And all we're doing now is rearranging this for dy on dx, right? We're asked to solve for dy on dx. So we'll take 4x to the 3 from both sides, divide both sides by 2y, and there's the answer. All right, part D. Find the slope of the tangent to the curve at t is pi on 6. So when the t value is pi on 6, what's the value of dy on dx? Well, here we have dy on dx in terms of x and y, and we've got x and y. So dy on dx is going to be minus 2 multiplied by the square root of cos of t. Now we're talking about when cos is pi on 6. And that's to the power of 3, okay? Minus 2x to the power of 3, and then on top of the y value, sine of pi on 6. Now this is only worth 1 mark, so we'll just evaluate that in our calculator rather than trying to simplify it using the unit circle and so forth. It doesn't ask for the exact value, so we're perfectly legitimate solution there. Minus 2, and then we have square root of cos of pi on 6, and then that's to the power of 3, and then that's divided by sine of pi on 6. Minus 3.223. Excellent. Now, as we're doing that, I'm going to fill in what calculations I have in the minus 3.22. Good. Okay, overleaf, we have question 3. We've got a complex number question. Okay, part A, 1. Write root 2 plus I root 2 in polar form. So straight to your calculator. You can type it in and convert to polar form. I'm looking at this going, the real component is the same as the imaginary component, so that means the angle is going to be pi on 4, right, 45 degrees. But nevertheless, what we'll type in our calculator, type this in, root 2 plus I root 2. And remember, I is where the 0 button is. You can press Shift I to bring that up. And what we do is we press Option, Complex, and then the across arrow. And then the one we're looking for is R angle theta. So if you've typed that in and then press this button and execute, we get 2 cis of pi on 4. Excellent. And then repeat for part 2. And I got 2 cis of minus pi on 4. Okay. Write z in simplest polar form where m and n are integers. So z, right, is 2 cis of pi on 4 to the power of m on top of 2 cis of minus pi on 4 to the power of n. Okay, so all I've done there is substitute the polar form in. Okay, and now we've got to write it in simplest polar form. So the way we're going to do that is we'll apply the complex number theorem where we distribute m and m here. So what we'll have, the top will simplify to 2 to the m cis of m pi on 4, m pi, and the denominator will simplify to 2 to the n cis of n pi on 4. Okay, so the 2 we can simplify using index laws. These have the same base, so it'll be the top power take the bottom power. We have 2 to the m take n. And then over here, all right, one of the rules of complex numbers is if we have cis of n theta on top of cis of m theta, that's equal to cis of n theta take m theta. All right, so now excuse me, that's negative. So if we're going to have cis of, and we have the top angle, m pi on 4, take the bottom angle, m pi on 4. All right, so in simplest form, we'll have 2 to the m take n, cis of m pi plus n pi on top of 4. Scrolling along. Alright, so that was B part 1. Okay, B part 2. State a positive integer value for n and a positive integer value for n such that z, this complex number z, this complex number is purely real. So if we think about the eigenplane, it's purely real here and here. So that's when it has an angle of 0, and that's when it has an angle of pi. 0, pi, 2 pi, 3 pi, right? So what we need is we need this angle here to simplify to pi. All right, so that's going to occur when both m and n are 2, we would get pi. Yep. If both m and n were 0, although we're asked for a positive integer value, so we can't use 0. So the first point is going to be when m and n are both 2. Could be something like m being 3 and n being 1. All right, so we're just asked any value for which it's true. So I'm going to go with if m is 2, then n is 2. And that's perfectly acceptable, even though here we'll have 2 to the power of 0. Well, that just simplifies to 1, right? So we still have a modulus out front of 1. It's still purely real. Other solutions, yep, m is 3, n is 1. That would work as well. All right, because that gives us a multiple of pi in here. Okay, so we've got 3 pi plus pi, that's 4 pi. 4 pi divided by pi simplifies to 4. Okay, and then for part 3, find values of m and n such that they're purely imaginary. So it's purely imaginary here and here, so that's multiples of pi on 2 and multiples of 3 pi on 2. So, like the lowest value for which it's going to be true is when both m and n are positive 1, because then we would have pi plus pi, we have 2 pi on 4, which simplifies to pi on 2. So m is 1, n is 1, and you can think of other values for which that would satisfy that as well. All right, does that make sense what that part's asking? Very good. Okay, we're flying through. On to question 4. We have a mathematical induction question. All right, so everyone remember induction? So I think the thing to remember from induction, all right, what we want to do, like we just follow state. That's how I've taught it. So it is state, test, assume, prove, and then explain. They're the things we need. All right, so firstly we need a statement. Use mathematical induction to show that this is true. All right, so we've got a divisibility one here. So we still make a statement about P of n. P of n, the proposition with regards to n, is that 2 to the power of 4n take away 3n is divisible by 13 for all positive integers. Okay, now remember we make a P of n, we make a proposition because the utility of that is that when we get down to our explain step, we don't need to restate the proposition, we can just say P of n. Okay, we can just say P of n is true. All right, test. Okay, so we've stated the proposition. Now let's test for the lowest value for which it's true. Now we're saying it's true for positive integers, so the lowest positive integer is 1. Test for n is 1. P of 1 is going to be 2 to the power of 4, take 3. That's 16, take 3, which is 13. Therefore, P of 1 is true. All right. 13 is divisible by 13. Okay, then we assume P of k is true. Assume P of k, and this is basically just a restatement of the proposition, but with regards to k. So assume P of k equals, now because it's divisible by 13, it's equal to 13 multiplied by some number. A is some integer value.
Do we also need to state that k is a positive integer?
Yes. K, comma A. All right. Assume, and then we're on to considering our P of k plus 1. Consider P of k plus 1. This is our proof part. So P of k plus 1 is going to be, now I will do it right here, 2 to the 4k plus 1, take 3 to the k plus 1. Now remember, what we have to do is we have to somehow substitute P of k into this. So let's take P of k over here, right? 2 to the 4k, take 3 to the k, equals 13a. That's our P of k proposition, and we can easily rearrange this for one of these terms. I'm going to rearrange it for this term. Doesn't matter which one you do, it'll always work out the same. Now the reason we've done that is because now we can substitute this term into here. Okay, so we can split that up. We have 2 to the 4k, I'll do it over a series of steps. 2 to the 4k plus 4, take 3 to the k plus 1. So all I've done here is expand that. Then what we'll do is we'll split it using index laws. Okay, now the index law I'm using is this one. We have a to the m times a to the n. That's a to the m plus n. So that means we're here, we can go back the other way. So we've got 2 to the 4k plus 4. We're going to write that as 2 to the 4 times 2 to the 4k. Right? That's the reverse of the index law. And we'll do the same with the 3. And now we can perform the substitution P of k. So using P of k, so I'm going to put that 13a plus 3 to the k. You can see it would work if you did the 3 to the k substitution as well. I'm going to plug that right there where 2 to the 4k is. So what do we have? We have 2 to the 4 multiplied by, and that's 13a plus 3 to the k. Okay, that's the substitution there. And then we have take 3 to the k times 3. And we'll just reference using P of k. And what we'll end up with, that's 16. So we have 16 times 13a. And then we have 16 times 3 to the k. Take 3 times 3 to the k. Okay, these are like terms. 16 times 3 to the k, take away 3 lots of 3 to the k. That leaves us with 13 lots of 3 to the k, of which 13 is now a factor of this expression. explaining, because P of 1 is true, okay, because our test case is true, and P of k plus 1 is true, if P of k is true, therefore P of n is true for all n is plus by PMI. Beautiful. What a beautiful proof that is. So PMI, right, make sure we get those marks, okay, 5 marks there. Yeah, they're not too, they don't tend to be too challenging, the PMI questions. So yeah, make sure we hit all the steps. Even then, remember, even if you get stuck here, you might lose some marks there, but you can still hit the explain step. You can say P of 1 is true, P of k plus 1 is true. Yeah, don't get bogged down in them either, okay? All right, part B, explain why 2 to the power of 2020 take 3 to the power of 505 is divisible by 13. Okay, so this is very clearly using what you've just done, all right? Observing the relationship you've just found out. We have 2 to the 4 and take 3 to the n is divisible by 13. And so then we're asked, well, what about this proposition here? So what we should see is that P of 505, all right, if we have n is 505, 4 times 505 is 2020. Okay, so then what we should say is because P of n is true for all n is e plus, therefore P of 505 is true. And so really they're only looking for a link between P of 505 and what they've expressed here. So very generous 2 marks there as well. Excellent. Okay. Getting scrolled in, but not that we're referring to it much. All right, we've done that one, we've done that one. So question 5. A cone is formed as grain is poured into a large cylindrical container of fixed radius. The volume of grain in cubic meters is given by this equation, where h is the height of the cone in meters, feet is in radians. Note that v, h, and theta are all functions of time. So we have 3 variables, the volume, the height, and the angle. All right, show that dv on dt is this. So we're starting with the volume is 1/3 pi h to the 3 tan squared theta. And we're asked to differentiate this whole expression with regards to time. Okay, so what we're doing is we're doing this whole thing with regards to time. So what we'll have, we're going to have dv on dt on the left side, and 1/3 pi, that's going to just be some, excuse me, pi's at the top. That's going to be some constant, right? And then we have h to the 3 times tan squared theta. So that's what we're going to differentiate with regards to t. H to the 3 tan squared of theta. Okay, so all I've done there is I'm localizing. We want to differentiate this component with regards to t. And so when I'm doing the product rule now, the utility of pulling the 1/3 pi up front is we're not complicating the product rule. We only have 2 terms. It doesn't make it much of a difference really, it just means you'll be using more ink. Alright, but we can pull the 1/3 pi up front, and now we've got u and v for our product rule. So we'll use the product rule here. We have u is h to the 3, u dash will be 3h squared dh on dt. V is tan of theta squared. So then we're using the chain rule there to differentiate tan theta squared. So V dash will be n, so 2 tan theta to the power of 1, and then multiplied by the derivative of tan theta. which is sec of theta. Okay, and so then we'll just smash all of that together. dv on dt is a third pi multiplied by u dash, excuse me, we need d theta on dt, don't forget that. All right, we've differentiated this variable with regards to t. U dash v, so we have 3h squared dh on dt tan of theta squared plus, and then u v dash all right, now we're getting pretty close. The only difference is that they've factorized h squared and the terms are written around the other way. So in brackets here we have 2h tan theta sec theta d theta on dt, and then plus dh, 3dh on dt tan squared theta. Why didn't we factorise tan theta as well? They haven't asked us to, so we've shown that that's true. Okay, part B. Everyone okay? Yep. Consider the instant when theta is pi on 6 and the volume is 3 pi cubic meters. Find h at this instant. Okay, so we're using the initial equation. So we've got third pi h cubed tan squared of theta. Now we're asked to find h given the volume is 3 pi and the angle is pi on 6. Alright, so all we're going to do is rearrange this for h and cube root, right? So this gives us h is the, we'll do h by itself first, 3 pi on top of a third pi of tan squared of pi on 6. Pi will cancel. We'll evaluate that. And cube root it. So what do we have? 3 on top of a third tan of pi on 6 squared. And the cube root of 27 is 3. And units are in volumes in cubic meters, so meters. So that was P part 1. At this instant, d theta on dt equals pi on 12 radians per second, and the height of the cone is decreasing at approximately 1.81 meters per second. Find dv on dt. So even if you haven't been able to show part A, you've still given the equation dv on dt. So that's what we're asked to find, right? We're asked to find dv on dt, given we've got h is a third. And let's list the other things we're told. We're told d theta on dt is pi on 12. And we have dh on dt, and the height of the cone is decreasing at 1.81 meters per second. So the height of the cone is decreasing. So how does that work? That's because it's moving up. Yep. So dh on dt is a negative value. dh on dt, because it's decreasing, minus 1.81. Excellent. So all we're going to do then is substitute all of these values into our equation here. So we have third pi times 3 squared multiplied by 2 times 3 tan. Now the angle is pi on 6, as we're told at this instance. Tan of pi on 6, sec of pi on 6. d theta on dt is pi on 12. oof, it's going to be a pain to type in. Maybe that's why it's worth 3 marks. 3, and then we have minus 1.81 tan of pi on 6 squared. All right, let's have a go.
The sec's meant to be squared.
Sec squared, is it?
Yeah.
Dang. It tells us that as well, does it?
Yeah. In the.
Alright. Sec squared. Thank you. That'll stop us committing an error there. Got sec squared written down here too. Alright, so what's this going to be? We're going to have 3 pi up front. And then in brackets, alright, we've got, we'll do this term first, we've got 6 pi on 12, which simplifies to pi on 2, 6 pi on 12, tan of pi on 6, sec of pi on 6. Now sec is 1 on cos, right? Yes. I think. Alright, close that bracket. Plus.
Yes, it is.
And then we have 3 times negative 1.81 times, and then we have tan of pi on 6 squared. Alright, so this is something that you should not rush typing all this in, okay? Because, yep, you get marks for substituting the values in. I would say you get 1 mark for substituting the value in, 1 mark for recognising this needs to be negative, okay? And the final mark for the correct answer. Now I've got 102, which seems really large. Didn't close my brackets. Still 102. 6 pi, 3 pi, times 6 pi on 12. Okay, I think it's doing the, alright, I've got to put more brackets in, excuse me. So pi on 6 times 1 on the cos of pi on 6. So that's the red part, and then plus 3 times minus 1.81. No, I'm still getting 102.499. Alright, let's write that for now. Might come back and have a look at that. Why am I getting 102? Meters. So volume's meters cubed, and time is in seconds. It seems like a really large volume, doesn't it? Just try one more thing. Huh. So whether the height is negative or positive, the answer's the same. How would that be? Alright, let's leave it. Okay, so this is an example of a place where we shouldn't get bogged down, and that's something that we can come back to. Okay, so you make a mark. Good example of when you get stuck on a question. If we spend any longer on it, we've spent too long on it.
I've got 20.6.
That still sounds quite large, doesn't it? Meters cubed per, what's the time period? Seconds?
Seconds.
I've got 2.6.
I reckon that sounds better. Although that still sounds quite large because I suppose the initial volume is 9.
You've got negative 5.
Negative 5? I don't think negative 5 is correct because stuff's being added. Okay.
4 of us got different answers.
Alright, wow. So let's move on. Now I'm saying be careful. But that's the annoying thing about typing in a long expression like that is you have one bracket in the wrong spot and it screws up the whole thing. Okay, so let's move on. Like I said, question 6. Alright, we have a functions question here. We have 1 on x take 2, take 1 on x plus 3. And we're asked, show that it equals 5 on x take 2 times x plus 3. Okay, so whenever we have these, remember, we have to communicate it clearly. We have to show all of the steps. So we state the left-hand side, perform the cross multiplication. And that leaves us with 5 at the top, the right hand side. Okay, then we have draw the graph of f of x on the axes below. Okay, so 5 on x, take 2 times x plus 3. So we can identify the asymptotes immediately, right? So we know there's going to be an asymptote at x is positive 2. All right, make sure we label it, x is 2, and an asymptote at negative 3. All right, and then we'll just refer to our calculator for the other features. So I'll go to Desmos. I can do it on the graphics calculator if you prefer, but this is going to be easier. It's just easier for me to type it in. 5 on x take 2, x plus 3. And so we can see our asymptotes at x is 2 and x is minus 3. And we can see the function there has a local max at minus 5 and minus 0.8. So make sure we get that in the scale. Okay. And then these other parts out here are doing this, aren't they? So when they have graphs, when they're allocating marks for graphs, they tend to pick on a few things. So for example, this solution, okay, this local max, they will allocate a box for which that local max has to occur in. Now on our paper, it'll probably be, it's sort of, it has to be in the top, the bottom, the box in the third quadrant, doesn't it? That's where it's going to occur. Has to be in that box, okay? And towards the lower end of that box. So we're getting a mark there, getting a mark for recognizing the asymptotes, and then just the general shape of it. Okay, very good. All right, so that's B part 1. B part 2, draw the graph of the modulus of f of x. Okay, so all the modulus of f of x does is make the function positive. All right, so any negative parts are just flipped up and become positive. So we still have these asymptotes here. So like that. This is positive, so it remains positive. We now have a local minimum, and we have that. So that's x, y, x is 2, x is minus 3. Excellent. So that's the modulus of f of x. And I'll sketch it here for you. Turn the first function off. So that's what we expect it to look like. Excellent. All right, on to the third one. Now draw the graph of the modulus of f of x, take away f of x. All right, the modulus of f of x, take f of x. Now your temptation here is probably to go straight to your calculator or to your Desmos, right? It's, in my circumstance, I've called it g of x, so the modulus function, take away f of x. All right, so let's sketch it, and then I'll make a few comments about it. All right, about how we can draw the graph of it and what features we should look for. Okay, so I'm looking at the black function, right? So it seems to be the line y equals 0 for values greater than 2, the line y equals 0 for values less than 3. All right, so we can draw that part. Now the way we would do that is we've still got these asymptotes here at x is 2, and we draw a circle to show that it doesn't exist at that point, but then it exists for values larger than that point. The same with minus 3. Okay. Now the reason that's the case, okay, if you think about what are we performing here, we're doing this function take away this function. So that means, remember, these parts are the same. So I'm doing this part, take away this part, they're going to cancel, right? And so that gives us y equals 0. The same on this side. That take away that gives us y equals 0. All right. But then what's going on with that local max? What we have is we have here, I have, like, just focus on that coordinate, for example. All right, so remember f of x is the y value. So there we have a y value of positive 0.8. So we have 0.8 take away negative 0.8. What's that give us? 1.6. All right, and so that's where the new local minimum for this function is. It's sort of gone up in height. 1.6, right? Still has the same x value. Okay. Now, find the exact area between the graph, so we're on to part C now. Find the exact area between the graph, y equals modulus of fx, take f of x. So the third graph, the graph we've just done, between x is minus 2 and x is positive 1. All right, so area under a curve, that's just the integral, right? So what we're evaluating is the integral from minus 2 to positive 1 of the modulus function. So what's it, 5 on x take 2 times x plus 3. Take the non-modulus function with regards to x. Okay, so that's what we're asked to evaluate. Now, there's two things we sort of need to recognize here. All right, it's the modulus of f of x, take f of x. Now, over the interval from minus 2 to 1, all right, the function modulus of f of x, take f of x, what is it equal to but minus 2 lots of the original function? Okay, let's explain why. All right, so if we look here, we've got 1.6 is the y value. Here was the original function. So if we go minus 2 times minus 0.8, that's going to flip it and provide it with that dilation factor. Okay, so what we're going to do then is perform this substitution. Now that's quite tricky to see. Okay, so you're getting a mark there for sort of that substitution to perform that mathematics. So what this simplifies to then is we're doing an integral from minus 2 to 1 of minus 2, and we can just bring that right out front of an integral, right? It's just a number of minus 2 multiplied by 5 on top of the original function, x take 2 times x plus 3. Okay, so that's quite tricky seeing that. Is everyone okay with that? All right, so they're the kind of substitutions that can take a little bit of time to figure out. Probably your temptation is just to grind this out, but we don't have a procedure for performing an integral of a modulus function. All right, so what we should be doing is, separating and recognizing that substitution. All right, then what we've got is we've got another substitution to perform, which is what we did right at the start. Remember, right at the start, we said, hence, show that this is true. So we've got to go back and perform that substitution that we performed so that we can integrate both components. So we have from minus 2 to positive 1, we have 1 on x, now I'll get the order of them correct. 1 on x take 2, take away 1 on x plus 3. Now both of those components we can integrate. We can't integrate this function, but there's a reason we showed they're the same. It's so that we can integrate it now. So that becomes ln modulus of x take 2, take away ln modulus of x plus 3 from minus 2 to 1, and then we're just substituting the numbers in. All right, so the minus 2 can hang out the front still for now. So we have ln modulus of minus 2 take 2. We sub in 1 first. Sub 1 in. 1 take 2. Take away ln modulus 1 plus 3. Alright, so that's when I've subbed in the upper boundary, take away. Now, so this part here, you're just doing that fundamental theorem of calculus, right? So just put upper boundary in, then the lower boundary in. Okay, simplify it. So ln modulus of 1 take 2, that's ln modulus of minus 1, and the modulus of minus 1 is positive 1, and ln of 1 is 0 anyway. Good. Then we have take ln of 4, we have take ln of modulus of negative 4, which is positive 4, and then we have take ln of 1. Alright, so the ln 1s are 0, they're going to just disappear. So we have, what we have is we have minus 2, and then minus ln 4 minus ln 4, that's minus 2 lots of ln 4. So this leaves us with positive 4 ln 4, which is the area under the curve. Alright, so there are tricky 3 marks to get. In an exam, there's easy marks to get, there's tough marks to get. Make sure we get the easy marks, and we've just got to try and get as many of the hard marks as we can. Alright, we're moving through it nicely. We're on to question 7.
For the question there, at the end it's minus ln of modulus negative 2 take 1. Wouldn't that be plus because of the minus in front of the bracket as well?
That one there? That one should be, yeah. That one should be, yeah. But ln of 1 is 0, so it'll cancel.
Oh, yeah.
Yep, good to go. Excellent. All right, use integration by, so question 7, use integration by parts. All right, so they're telling us how to do it. Use integration by parts to find the integral of x e to the 2x. Okay, so we have the integral of x e to the 2x. Now for integration by parts, let's write out the formula. It is the integral of uv dash equals uv take the integral of u dash v. Is that correct? I'm not sure. I've written that down properly. We always get dashes around the wrong way. Integration by parts. uv dashed equals uv take u dash v. Very good. Okay, so what this means, right? And remember what we're looking for is we want and v dash. V dash needs to be easy to integrate. The u needs to be easy to differentiate. So we can go either way here, except if we go this way, what we'll have u dash v, and that's something that we can integrate. If we do the opposite, we won't, because we'll have another x squared or 2 here. So there's only one way it is going to work. It's this way. U dash, and v dash is going to be e to the 2x, and the integral of e to the 2x is half e to the 2x. Okay, so this is uv dash. All right, we recognise that that's going to be our v dash term, that's going to be our u term. So let's smash all that together. I'll do it over here. We'll have, so the integral of x e to the 2x is uv, so what's that, half x e to the 2x. Take away the integral of u dash v. And the integral of half e to the 2x is just a quarter e to the 2x plus c. Now, is everyone okay with those integrals? Doing them? Yep. Excellent. Excelente. Okay, then we have another one. Use integration by parts to now show that this is true. All right, so this time we have the integral of x squared e to the 2x. All right, so same again now. U dash, v dash. Now what I'm thinking of here is that when we perform it, like maybe I'll just show you and then show why it's true. And v dash is e to the 2x, and this gives us half e to the 2x again. Now what's going to happen here? Oh, let me keep going even before we x squared e to the 2x. So we have take the integral of Okay. Give us a second, and we'll just do one more step. So we've reached this step, right? And the connection we should be making is that that's what we processed in part A. We did the integral of x e to the 2x in part A. Here it is here, the integral of x e to the 2x, and this is what it simplifies to. So we already know what the integral of x e to the 2x is, so we're just going to take that and chuck that in. So for our final answer of the integral of x e to the 2x, of x squared e to the 2x is half x squared e to the 2x, and then take away this thing here. Half x e to the 2x plus a quarter, plus because the negative negative, e to the 2x plus c. Alright. Everyone okay with that? Seeing the link there? Jack, you good? Yep, Haley? Excellent, okay. So then on to part B. Let f of x equal x e to the x. Alright, the graph is shown below. Find the exact volume of the solid obtained when the region bound by the graph over the interval 0 to 1 is rotated around the x-axis. So, for volume, it's integral from a to b of pi times the function squared. Alright, so in this circumstance, we're doing the integral from 0 to 1 of pi times the function x e to the x squared. Alright, which gives us, we can pull the pi up front, 0 to 1 of x squared e to the 2x. Okay, so hence why we had the integration by parts before, and hence why it even gives you the formula. So even if you haven't been able to crack part A, 1 or 2, you can still do part B here. Alright, so there's part B. So all we're going to do then is this integration. We know exactly what it integrates to. So it's going to become pi, and we have half x squared e to the 2x. Take half x e to the 2x plus a quarter e to the x. From 0 to 1. Sub in our upper boundary. We get half e to the 2. Take half e to the 2 plus a quarter e to the 2. So that's when we sub 1 in. Now when we sub 0 in, right, this term's going to be 0, this term's going to be 0, but this one is not. Alright, this one's going to be e to the power of 0. These are 0 because they have a 0 out front, so whenever you multiply it by 0, that's going to 0. But here we have e to the power of 0. So that one simplifies to a quarter. Alright, half e squared, take half e squared, they cancel. So we're left with pi times a quarter e squared, take a quarter. Something like that. Exact volume. Alright, everyone good? Okay, so let's move on to question 8 then. In booklet 2, we have a vector question. Time for a new marker, I think. Black's starting to get a bit faded. Okay. Consider the system of equations shown below. Write this system as an augmented matrix. Okay, so one mark for getting rid of the x, y's, and z's. So we've got 1, 2, 2, 2, 1, minus 2, 3, 2, minus 2, 4, 5, 8. Alright, talking talk about easy marks to get, right? All right. Stating all row operations show that the system of equations has the following solutions. Okay, so what this means is break it down using row operations to find out what's the solution to this augmented matrix. So remember, step one, get a 0 there. Okay, we're trying to get a 0 there, so let's do that. We're going to replace row 3 with 3 lots of row 1. Take row 3. All right, 3 times 1, take 3. That gives us the 0, right? So, state what we've got. Row 2 remains the same. So 3 take 3, 0. Then we have 6 take away 2, that's going to be 4. And we have 6 take away minus 2, that's going to be 8. And 12 take away 8, that's going to be 4. 4, 8, 4. Okay. Next step, so step 1, always try and get a 0 in that position.
This is a test PA announcement. This is a test PA announcement.
Then step 2, we're looking to get a 0 in that position. So we'll replace row 2 with 2 lots of row 1, take row 2. So row 1 remains the same, 1, 2, 2, 4. And row 2, 2 times 1 take 2, 0. 4 take 1, 3. 4 take minus 2, 6. 8 take 5, 3. And then we have here 0, 4, 8, 4. Okay. Now, what I'm looking at is seeing a direct relationship between these two. I'm seeing they're going to cancel one another. Now, one way we can really draw it out to really point out how they are the same is to replace row 2 with a third of row 2. So we're just going to multiply it by a third and replace row 3 with a quarter of row 3. All right, so it's going to maintain the same equation. Remember, what is a row, but it's an equation. And so you're still maintaining the equality because you're just multiplying both sides of the equation by a quarter. So that's an absolutely legitimate operation. 1, 2, 2, 4, and we'll have 0, 1, 2, 1, 0, 1, 2, 1. So you can see that they are the same plane. Okay, they're the same system. So then what we'll do is we'll replace row 3 with row 2, take row 3. And so then what that's going to leave us with is 1, 2, 2, 4, 0, 1, 2, 1, 0, 0, 0, 0. Okay, so then if you think back, I'm going to pull our vector booklet out here and describe what kind of solution we're approaching. So we have planes intersecting. And remember, there's 3 planes. Here are the 3 planes. And we've got the solution of 1, 2, or 7, okay? Because we have all rows at the bottom there. Now, the planes are not coincident because they're not the same, not all 3 of them are the same plane. So it's not 1. 2 of them aren't even the same plane, so it's not 2, which means it has to be 7, that all 3 planes meet along a common line. And what we're doing then is finding the equation of the line. So the way we find the equation of the line is we go let z equal t. That's the parameter for the z value. Then we solve now for y. We have 1 lot of y plus 2 lots of z equals 1. So that's y plus 2t equals 1. Y equals 1, take away 2 lots of t. And then we substitute that into the top row to solve for x. So we'll have x plus 2 lots of y plus 2 lots of z equals 4. we're just solving for x. So what's that give us? 2t, 2 take 2t. And it tells you the solution anyway, right? It says show that the solution is this, sorry, 2 plus 2t. Where did I? 4, yeah, 2 plus 2t minus 2 plus 4. It tells you the solution, so we won't get that wrong. Okay, using the information in A part 1, show that the points A and B are common to all 3 planes. Alright, so scroll down there. So we have 2 coordinates, and it says show that these points A and B are common to all 3 planes. Now, this is where quite often, there's questions where there's an easy way of doing it, and sort of it requires a bit of insight, or there's a long way of doing it, which just takes time. So what you're required to show is that point A, which is 2, 1, 0, and point B, which is 0, 3, minus 1, satisfies all 3 equations of the plane. So one way to do that, the long way to do it, would be to take the coordinates A and substitute them into plane 1, plane 2, plane 3, and show that left-hand side equals right-hand side, and then do the same with plane B. That's 6 calculations, right? That's a long way of doing it. So you must think there must be an easier way to do it. Now, if these points lie on all 3 planes, that means they lie on a point that is shared by all 3 planes. Okay, now what we found here, this is the insight, is we found all 3 planes intersect along a line, z, y, and x. And so that means if these points lie on all 3 planes, it means they have to lie on this line. Okay, so here's what we do. We go taking the line, so maybe we make the argument first. So like what can we say? So we can say like common to all 3 planes. So the line, are we told to find a line, or we can just define the line? So the line from part B, part A, part 2, sorry. Line from A, part 2, common to all 3 planes. Therefore, A and B lie on line. And then we'll go, all right, if t, the parameter t is 0, all right, if the parameter t is 0, the line is going to be, and we can sub it in, 2 plus 2 times 0 for x, 1 take 2 times 0 for y, and 0 for z, which is 2, 1, 0, point A. And then for point B, I'm subbing in t is minus 1. And so we have 2 plus 2 times minus 1. 1 take 2 times minus 1. And minus 1. Positive 3. And minus 1. Alright, so that's probably the fast way to show it. Although it's not much faster really, is it? They haven't given you much room there to show that it's common to all 3. Now, however, it does say using the information given in A part 2. So depending on the marking scheme, they may not give you full marks for the long process because it says with reference to A part 2. All right. Moving on, B part 2. Show that plane 1 and plane 2 are perpendicular. Okay, so plane 1 is perpendicular to plane 2 if the direction vector of plane 1 and the dot product of the direction vector of plane 2 is 0. All right, so P1 is 1, 2, 2, and P2 is 2, 1, minus 2. All right, turn the page. We got a diagram. Figure 8 shows point C on plane 3 and point D on plane 1, and the line L, which goes through C and D, intersecting plane 2 at point E. Okay, find in parametric form the equation of L. Okay, so find the equation of a line from C to D. The equation of a line from point C to D, which is minus 12 minus 4, 0. All right, so for the equation of a line, we need two things. We need an initial point and a direction vector. So let's find the direction vector from C to D. Do the coordinates of D, take the coordinates of C. So that's going to be 12 minus 10 and 0, take 2 minus 2. And we could simplify that, make it a scalar multiple. So therefore L has equation, well, it passes through point C. We need a new parameter, let's use lambda. And then the direction vector, well, let's simplify it, 6 minus 5 minus 1. Okay, find the coordinates of E. All right, well, E occurs when line 1, all right, the equation of this line satisfies the equation of plane 2, all right, because E is the point of coincidence of the line with plane 2. So plane 2, right, plane 2 has the equation 2x plus y take 2z equals 5. 2x plus y take 2z equals 5. All right, that's the equation of plane 2. And we're going to sub in, the coordinates here from the line. Now, one thing to be careful of that I've just noticed, it says find in parametric form. At the moment, we've stated it as vector form, okay? So just to simplify it to parametric form, x is 6 lambda, y is 6 take 5 lambda, and z is 2 take lambda. All right, so just something to be picky on there for C part 1. Yeah, C part 1, C part 2. So what we're going to do then is we're going to substitute the equation of the line into the plane to determine when the line meets the plane, right? That's going to give us a value of lambda. So let's evaluate that. We have 2 times 6 lambda plus 6 take 5 lambda, take 2 times 2 take lambda equals 5. So just subbing these values, the equation of the line, into the plane, and we'll simplify. 12 lambda plus 6 take 5 lambda, take 4, what does that say? Take 4 plus 2 lambda. All right, collecting like terms, we have 12 plus 2 is 14, take 5 is 9 lambda, and then we have 6, take 4 is 2, so we have 2, remove the 2 onto the other side, we get 5, take away 2, we get 3, we get lambda is a third. Now when lambda is a third, the line has the coordinate. When lambda is a third, we have x is 2, y is 6, take 5 times a third. So for those fraction operations, you know, starting to get late in the exam, it's like, I'm not even going to try to do that in my head. I'm just going to go 6, take 5 on 3, I'll go straight to my calculator. And I'm going to clear the big calculation we did before so I can try again later. 6 take 5 times a third, and so we've got 13 on 3, and 2 take a third. Well, I can do that one, that's 5 thirds. Alright, so that's the coordinates of E. Everyone okay with finding E? So what have we done? We found the equation of the line. We know that point E occurs when the line satisfies the equation of the plane, and so we found the value of lambda, and then we had to substitute lambda in to determine the coordinate on the line that has a value of lambda of a third. Okay, part 3. Find the distance from E to plane 1. Alright, distance from a point to a plane. This is a formula. So let me flip through my vector notes book and find that. It's late in the vector notes book. Planes on page 48. we have the distance from a point to a plane is the modulus of ax1 plus by1 plus cz1 plus d on top of the square root of a squared plus b squared plus c squared. Okay. So, in this circumstance, we have coordinate E, which is 2, 13 on 3 and 5 on 3. And we're finding the distance to the plane, distance to plane 1, which is x plus 2y plus 2z equals 4. Okay, so to sub it into the formula here, the distance is a times x1. So this is a, right? The coefficient of the x term, a. So we have 1 modulus 1 times the x value plus 2 times the y value, and then plus 2 times the z value, and then we have, when we move the d value over, right, plus 2y plus 2z, take 4 is 0, the d value is minus 4. Alright, so ax plus by plus cz plus the d value when we've shoved it over, all on top of, and then the square root of a squared plus b squared plus z squared. Alright, let's evaluate that. Should be just larger than 1. So we have 2 plus 26 on 3.
Why is it negative 4?
So here's the equation of the plane. When we want all of the terms on the same side, we have to take 4 to bring it over. So we have ax plus by plus cz plus d equals 0. So that's what you call the general form of the equation. Plus 26 on 3, plus 10 on 3, and then take 4. So that's 10, so we have the square root of 10 at the top, and at the bottom we have 9. Sorry, not the square root of 10, it's just the modulus of 10 at the top. 2, modulus of 10 on top of, and then this is the square root of 9 at the bottom. So we have here 10 on 3, 3.3 recurring. Cool. 1 plus 2 plus 2, that's 4, 8, 9. Good. All right. So let's move on then to D. All right. So this is where it gets a little bit confusing. The equations of P1 and P3 are used to model 2 hillsides that meet at a river as shown in figure 9. We've got the equations there. The river is modelled by the line where the 2 planes meet. A straight bridge modelled by L connects C and D. So we've already found the equation of the line that connects C and D. All right, and then we've got plane 1 and 3. Point E on the bridge must be at least 1 unit from P1 and P3. Does this model satisfy the condition? Show calculations. All right, so we've already seen that the distance from E to plane 1 is 3.3. All right, so that's going to be our first point. So from C part 3, so therefore it's satisfied. Okay, so it's more than 1 unit from E to plane 1. So all we need to do is go, well, what's the distance from E to plane 3? And so we'll do that calculation here. plane 3 is 3x plus 2y take 2z. Okay? Alright, so same distance formula calculation. We have the modulus of 3 times the x value plus, and then we have 2 times the y value, and then we have take 2 times the z value, and then we have take 8 modulus. Top one. Rewrite this. So what have we got? 6 plus 26 on 3. Plus take 3 on 3. Take 8. So at the top we have 10 on 3. Bottom we have the square root of 9 plus 4 plus 4. Square root of 17. (0.801), which is not larger than 1. Therefore, it does not meet the condition. Alright, we'll spell it out clearly. It does not meet the condition as e to p3 is 0.801 units. Very good. Alright. Alright, still got a bit to do. A little bogged down there. Okay, question 9. Solve the equation z to the power of 3 equals 1. Alright, so nth roots of unity, we have z to the 3 equals 1. First we're going to express 1 as cis of 0, and then we'll apply De Moivre's theorem. So just stating a cis of minus 2 pi on 3 because solutions on the eigenplane must lie between minus pi and positive pi. Very good. Okay, draw the solutions on the eigenplane, labelling each solution in an anti-clockwise direction, A1 through to A3. Alright, so the trick here, guys, is they give you a really simple task to do, right? Draw these solutions. So you're going cis of 0, that's there. You've got cis of 2 pi on 3, that's there. And we know they're all a third apart, right? Cis of 2 pi on 3. So that's fairly straightforward, but I think the trick comes in following the instructions. Labelling each solution in an anti-clockwise direction, A1 through to A3. So here's our first solution, second solution, third solution, going anti-clockwise, where A1 is real. We're told that. Okay, explain why. Now this is quite difficult to articulate, but it's only worth 1 mark. Explain why A2 lies on the line with equation z take A1 equals z take A3. So what we should say is the line z take A1 equals z take A3. This is what we call the diagonal bisector. Like it's exactly halfway between the 2 points, A1 and A3. So this line is the diagonal bisector. Halfway between All right, and then we're going to say as z to the 3 equals 1 has 3 solutions that are equally spaced, A2 lies on this bisector. Something like that. All right. Then we get a couple of easy ones. So we have evaluate A1 plus A2 plus A3. All right, so there's a couple of ways you can do it. You can think about it as a vector argument. If I go A1 plus A2 plus A3, I end up back at 0. You can type these in your calculator. Cis of 0 plus cis of 2 pi and 3 plus cis of minus 2 pi and 3, you get 0. Okay, so the answer to this part, which is A part 4, is 0. All right, then we have A part 5, evaluate the modulus of A1 plus the modulus of A2 plus the modulus of A3. Well, the modulus of each of these is 1 unit. So we have 1 plus 1 plus 1, we have 3. So a couple of easy marks there. All right, find the exact value of the modulus of A2, take the modulus of A3. So here, part 6, far out. Here I'd be going to our calculator and going, what is the modulus of, and we have A2, A2 is cis of 2 pi and 3. Take the modulus of A3. All right, so what we're doing here, we can convert these to Cartesian form and then just evaluate the modulus of it. That's going to be the best way for us to do it. So now, if we do that as well, maybe I can start to indicate an argument that's going to occur here. Notice how, at this point, they have the same real value, all right? The real value is, now it's 2 pi and 3, so the real value is going to be half, right? And so when you're doing A2, take A3, the real value cancels, yeah? Like even let's find, if we have 2 pi and 3, we have half and root 3 on 2, and we have half here and negative root 3 on 2. So if we do the Cartesian form, 0.5 take 0.5, that cancels. Root 3 on 2 take negative root 3 on 2, that's root 3 on 2 plus root 3 on 2, we have root 3. So the modulus is going to be root 3. So you can think about it in the calculator, you can think about it normally. The modulus is root 3. Okay, consider the equation w take 1 to the power of 3 equals 1. Show that the solutions to this equation are. All right, so if we have w take 1 to the power of 3 equals 1. All right, so what we have is we have w take 1 to the power of 3 equals, so we would have w take 1 equals cis of 0, cis of 2 pi on 3, and cis of minus 2 pi on 3. That's what we did in part A. And so then w is cis of 0 plus 1, which is A1 by the way, 1 plus A1, 1 plus A2, and 1 plus A3. Draw these solutions on the Argand plane. So the only thing that's happening here is we're shoving them over a little bit. All right, so if you think, here's A1, and if you add 1 to it, okay, so that means this point here is moving 1 unit to the right, all of a sudden A1 starts here. All right, if you add 1 unit to A2, all right, we're shifting it 1 unit in the real direction, A2 goes here, and A3 goes here. Now we can sketch them up a bit better, like that's going to have a value of half. That'll be half as well. There's half. Alright, draw the solutions of w take 1 to the power of 3. Done. show that W2 and W3 line on the line, the real part of Z is half. Okay, so if we think about W2, alright, so W2 is this one, 1 plus A2, which is 1 plus cis of 2 pi on 3, which is 1 plus, and cis of 2 pi on 3, well that's negative half plus root 3 on 2, which is half plus root 3 on 2. Therefore, the real part of W2 is half. Okay, so that's what we're doing. We're making two arguments there. One for W2 and the other for W3. And so I was alluding to that before, right, when I was pointing out the half and the root 3 on 2. So that's going to be 1, take half, take root 3 on 2, I, sorry, I should have i's here. Alright, so therefore they line all line with a real component of half. Alright, evaluate the modulus of W1 plus the modulus of W2 plus the modulus of W3. Alright, so the modulus of W2 and the modulus of W3, they're both 1. So we have the modulus of W1 plus modulus of W2 plus modulus of W3. So that's 1, that's 1. But this one, the initial one, W1, is actually 2. So if you think W1 is 1 plus A1, which is 1 plus cis of 0, and cis of 0 is 1, so it's 1 plus 1, it's 2. The modulus of 2 is 2. So that's a little bit tricky there, all right? So the answer is 2 plus 1 plus 1, which is 4. All right, last one. Find the exact value of W1 take W2 plus W2 take W3 plus W3 take W1. All right, so I reckon the best procedure here is going to be Cartesian form on our calculator. So, like if you think if we have W1 take W2, but let's do that first. W1 take W2, the modulus of that. What we'll have is we'll have 1 plus cis of 0, that's W1, take away 1 plus cis of 2 pi on 3, and we're asked to find the modulus of it. Okay, now 1 and 1, they're always going to cancel. Alright, so we're just left with cis of 0 take cis of 2 pi on 3, and so in Cartesian form, this is the number 1, take away, and this in Cartesian form is half plus, negative half, sorry, plus root 3 on 2, modulus of that. And so keep breaking it down, we have 1 plus a half, so that's 3 on 2. So we have the modulus of 3 on 2 plus root 3 on 2, and we'll just square root.
Wouldn't it be take root 3 on 2?
Take root 3 on 2, thank you. Yeah, so that's positive, that one's negative. So we have 9 on 4 plus 3 on 4, that's 12 on 4, which is square root of 3. Alright, so W1 take W2 is square root of 3. And the others are going to be the same. Alright, so W2 take W3 take W2, and W3 take W1. So the answer here is 3 lots of root 3. Alright. Now I've only checked one there, alright, but you can check the others in your calculator pretty straightforward. Like even if you just type in the Cartesian, the polar form, it'll still work out as well. Very good. Okay, let's move on to the last one. Question 10. So we have a differential equations question here, and we're doing well. Alright, in an experiment, one type of bacterium called alpha was grown in a petri dish. the rate of change of the area of the Petri dish that was covered by alpha bacteria can be modelled by this differential equation, where A is area in centimetres squared and T is time in days. At time is 0, the Petri dish was covered by 1 centimetre of area. On the slope in field in figure 12, draw the solution curve. Alright, so I wonder if I can draw on here using my pencil to show you guys. So what we do, yep, it goes through x is 0, y is 1. That's our starting point, and then we're just tracing up. Let's see. Edit, draw.
On the right, top. Is that a pen? Go up next. Yeah, and then left. Yeah, one of those things.
Alright, sign, highlight. Nah. Nah, all good. Anyway, you guys know how to do that, right? Okay, so we don't cross a line, we just follow the curve up as it goes. Here's the one that I drew the other day. That's what it should look like, approaching an asymptote.
Nailed it.
So 3 marks, all right? So again, make sure
How'd
you
you
don't
do it
cross a
so
line,
clear?
right? You're just following the curve along. So I would say you get 1 mark for the initial point, 1 mark for following the asymptote. And then because this is a logistic function, it has a point of inflection that occurs exactly halfway. So the maximum value is 50, so the point of inflection should be occurring around the y value of 25. Okay, let's go to part 1. A part 2. Show that this is true, so we have another show that. So we'll start with the right hand side this time, because that's the side we're going to manipulate. So we have the right hand side is 1 on A plus 1 on 50 take A, and then perform the cross multiplication.
I like this question.
Really drawing it out, which is 50 on top of A times 50 take A. Very good. Right, then we get one of these rip snorters. Solve the differential equation. Alright, so it's almost the same as what we have, except the differential equation has a half, doesn't it? So we have show, scroll down so we can see. Solve the differential equation. dA on dt equals half A, and here we have the 50 on A times 50 take A. Otherwise, that 50 take A times A. No, the A is there. On top of 50. There we go. Alright, so we're going to solve this differential equation. So looking here, right, it's everything except the half, isn't it? So I'm going to multiply both sides by 50 on top of A times 50 take A. That gives us dA on dt, and on the right hand side we will have half. Okay, so I'm just taking this term, flipping it, bringing it over here, I'm leaving the half on the right hand side. Okay, we will integrate both sides with respect to t. So what we have then is we have 50 on A times 50 take A with regards to A, with regards to t. Performing the substitution, we know that this is 1 on A plus 1 on 50 take A with regards to A. Alright, so that gives us ln modulus of A, take ln modulus of 50 take A. And on the right hand side we have half T plus C. So that's going to give us ln modulus A on 50 take A. Hi there. Yeah, thank you very much. Thank you.
I'm having fun with that thing.
Equals half t plus c. Then we'll raise e to the power of both sides, right? So we'll have a on 50 take a equals plus or minus e to the half t plus c. Even then I might split it straight away, plus or minus e to the c, e to the half t. Okay, then what we do is we put both sides to the power of -1 so that we can split the denominator on the left hand side. It's very clever. And so we make both powers negative on this side. And we perform some substitution for e to the minus c. Let's go with the letter p. Pause there, probably going a bit quick. Alright, then we +1 to both sides. And then we swap the a with the 1 plus PE. Alright, so that's the differential equation, but it says show that the solution is this, and so we have to use the information with the initial condition, which was a of 0 equals 1. So that means when we put so down the bottom here we've got 50 on top of 1 plus p equals 1. So therefore p is 49. Therefore a is 50, 49. Alright. Beautiful. So can almost guarantee there'll be one of these questions. There's a whole booklet on them. Make sure we hit them. They're all ever so slightly different, but the general process is very similar. Okay, so then we have state the maximum area that's available for growth. All right, so the horizontal asymptote is 50. It won't go past 50, and that's also observable in the graph of the differential equation slope field that we looked at before. Alright, so that's the answer to part 4 is 50 centimeters squared. Alright, when t equals 1, a different type of bacterium called beta was accidentally introduced to the petri dish. Someone sneezed on it maybe. Beta bacteria grew more quickly than alpha bacteria. The area B in the petri dish that was covered by beta bacteria can be modeled by this equation, where D is time in days after the beta bacterium was introduced. Figure 13 shows the graph for the area of the petri dish covered by beta bacterium, D days after beta bacterium was introduced. Part 1. Find D and B when the rate of growth of beta bacteria was at its greatest. Okay, when is it fastest? So there's a couple ways to think about this one. Like if I bring that graph up, a couple ways to think about that. All right, when is the rate at which it's changing fastest? All right, so that's going to be when is the slope steepest. That's a point of inflection. Okay, so we can do a point of inflection by graphing the derivative and g solving the max. Okay, that's when it's steepest, when it has the steepest slope. Or we can use our knowledge of a logistic function. If we look at our notes books at what a logistic function is and the properties it has, it tells you the coordinates of the point of inflection. Now, the point of inflection always occurs halfway between the are always half of the horizontal asymptote. So the horizontal asymptote is 50, right? That's the horizontal asymptote, which means the point of inflection therefore occurs at 25. So we want to know what's the x value when the y value is 25. So find D and B. All right, so B is 25, that's where the point of inflection occurs, and we want the corresponding x value. So what I'm going to do is graph the function 50 on top of 1 plus 79 e to the minus 5. So I'll get rid of all these. So we have 50 on top of 1 plus 79.
0.87.
Nice.
Seth put a guess in.
Yeah, what a guess.
Was
E to the minus 5x. And we want to know when x is, when y is 25. So we'll stretch y out to not that high. And if I go y is 25, the x value is 0.874. Very good. So we have D, because on the x-axis we have the variable D, which is days, 0.874, and on the y-axis we have 25. Now, one other way you could do this, right, is you've got the function. I want to show you what it corresponds with. So let me define this function as h of x. And then if we graph the derivative function, okay, we know how to do that from methods, right? Look where that maximum point occurs. Okay, so the x value of the when the rate of change is maximized, 0.874, 0.874. Okay, so they're the same.
We can't see what's on there.
Oh, sorry. Why is
Yeah, but
that?
inflection points become.
Could you not see any of those graphs I was doing before?
No.
No.
What? Why didn't you say anything?
I didn't realise you were graphing.
Busy catching up.
I'm trying to do it for you guys. To duplicate. Is that what I want? Is it frozen? Oh well. I think that's frozen actually.
Yeah.
It's just graphs popped up before when we were
Yeah.
pointing at them. Yeah. All right, we're almost done. So we've found D and B. We get 2 marks there for finding D and B. All right. Find the area of the petri dish covered by alpha bacteria when the rate of growth of beta bacteria is its greatest. Okay, so we know beta is greatest when D is 0.874. Now the trick here though, there's a little trick, is that beta bacteria is added exactly 1 day after A starts growing. So that means in terms of the model we've found in part A3, so we found the model was 50 on top of 1 plus 49 e to the minus half t. Okay, that's the model we found. Now, D is 0.874, but D starts when t is 1. So that means the t value we're going to put in here is 1.874. Okay, so we're subbing in t is 1.874. Find the area when it's at its greatest. So the t value is 1.874 and the area of 1.874 is 2.48 centimeters. All right. Lastly, when the petri dish is completely covered by bacteria, which type of bacterium is likely to cover more area? So if we have a look, right, we've got, after 1 day, all right, look, beta bacteria has covered, what, 35 centimeters, okay? And if we flick back and we go, after 2 days, bacteria A has covered 4 centimeters. So we can see beta bacteria, someone's got some high quality sneezes, is growing a lot faster. The answer there is beta. All right, good. So, excellent. We did it all in 1 hour 50. So you've got 20 minutes left to go and check your stuff, right? Now there was one thing we need to fix though, wasn't there? So I'm flicking back to that. That was question 5. And I'm going to make sure I just type in exactly what they have for us. I'm just going to type in everything the exact same. A third pi of h squared. Now we found h was 3. Yeah, third pi h squared, and then that's multiplied by 2 times h, so that's going to be 6 tan, and the angle is pi on 6. Alright, everyone try again. 6 tan pi on 6 by sec of, whoops,
Oh, 6 squared.
oh, did we not square it?
6.
Sec squared times d theta on dt, which is pi on 12. Alright, have I got that first part right? So we have, I'm just checking the first part, we have 6.
What colour comes after?
Tan
Green.
pi
Oh,
on 6.
red again. That's boring.
You've got to multiply everything by
Yo.
3 pi there, right?
Purple.
Out the front,
Yeah.
yeah, a third pi, and then h squared as well.
Bro, look at that.
Which comes out
Like
to 3 pi,
that.
right?
Yes.
Yeah.
Yeah, I agree. That's what I did before, but it didn't work, so I've typed it all in
Alright.
properly. 3 times, and then we have dh on dt, which
Oh,
is minus 1.81.
Three times.
I reckon I've just nailed that. I have the same answer as before.
Well, I reckon you have 10 of. You were following my instructions when I said be careful. Shift pi, root pi.
Oh, it
6.
took me to. Don't worry, I'm back. I'm back. No need to worry, lads. Okay, this I'm seeing a lot more bracket cut. Okay, got the exact same thing as before.
I got minus 18 that time.
Nice.
Pi h squared, alright. Have a look.
Let's-
6.
Put that out the front.
That's 2 times 3.
Okay.
Haley, what are you getting? I feel like you're left out.
She's letting us do the hard work. 10 of pi on 6. 1 of cos. Let's put a bracket there actually. Let's bracket all that together.
Okay, let's do that.
What's the difference between what we've put in? Oh, easy. Alright, go through.
Didn't want you to
So
steal
1/3 pi, yeah. 3 squared,
Yeah,
6.
I'll just put in 6.
Minus 18.
10 pi on 6 times 1 by 6.
Squared.
That's the same, yeah.
Yeah.
Times pi on 12
Yeah.
plus 3 minus 1.81. 10 pi on 8.
Is it pi on 8?
Oh, maybe that's where I go, huh? Is it,
So it's pi on 6.
I've written pi on 8 here, that's why. So pi on 6, there we go. Squared.
What have
So
you
now
got?
I got
Jack?
the
I've
same.
converted him.
What'd you get? 2?
I got negative 7.1.
Oh my gosh.
I did have
Imagine
20
marking this
before,
exam.
Yeah,
but
cheers.
You did what?
I had 20 before, but I was missing a bit.
Radians per second.
Well, I got 10 squared. I didn't square the end of it.
Well, both Jeff and I have negative 5.66. So
Oh, I got
what was-
negative 5.66 as well, just then.
What was the angle meant to be? Was it pi on 6 or what?
I reckon the. No, that's not right either.
What's
The
it say,
angle.
the angle?
I'm pretty sure the angle is pi on 6, isn't it? When theta is pi on 6, v is 3 pi.
Yeah.
And then it's at this instant because it's the same
Yeah.
part as before.
Is the volume decreasing?
The height is decreasing.
Cone is formed as grain is poured in.
Do you have the solutions to these
Yes, I do.
on the OneDrive?
Yep.
Oh, then I just got 28 because it made the 1.8 not needed.
Yeah, same as that's what happens when you do that. So what's going on here? Let's have a look.
God, I can go for a Zinger stack box right now.
So what's the new code?
I haven't had breakfast. So I've had a shower, came here.
6553. Let's find out what we're doing wrong, huh?
How do you still haven't told us what you got?
I've got 2.62.
That sounds good.
That's
What you got before, or that's what you have?
But that's what, yeah, when I did that though, I put in 0.8 for one of the angles by
Oh.
accident.
Oh,
So the second angle.
second angle.
Well, that was the second time I did it.
Why
I don't know
why'd you put 0.8?
I'm gonna click
So,
that.
anyway, guys, when you get stuck in the exam, what you do, just pull your OneDrive out, have a look at the solutions, and what's it, 12 Spec Maths exams.
I got like a very detailed.
Sample 2020.
I reckon this is.
Oh, thanks, I appreciate that.
Solutions.
You have nice quads.
Put it there, pal. That's like the best compliment I can get, I reckon.
2018, 2019.
It's 5B2. 5B.2.
What year is this test?
2020.
Oh, there's that question. Is it? No, that's a different. Wait,
It says 2017, didn't it?
Oh yeah, yeah. It's all a bit jumbled up. I think. There's the vector question.
Yeah, it's a bit before that.
Oh look, minus 5.66.
Oh, look at that.
We shouldn't have doubted ourselves, guys.
I got that initially. I got
So-
that the first time.
That was tough.
That's a bit confusing, isn't it? The
Definition
volume
of
is
colours.
decreasing because the height's decreasing. You've got to trust yourself. That's the message here.
Wait, yeah, so what did we actually just calculate?
The rate of change of volume.